All right, so here we are in what I guess would be lesson 20 for our class this semester, where we take something like this and we graph it in polar coordinates. Okay, so quick mistake. That should be r. In polar coordinates, you have r and theta, so that should have said r is equal to 1 plus cosine theta. So if we were to draw this in polar coordinates, there's several ways you can do it. You can make a table and plot the points one at a time, assuming you know what polar coordinates are. You could, I don't know, let's do what I really intend you to learn in lesson 20, which is draw this in rectangular coordinates and then convert those points in that pattern into polar coordinates. Let's do it that way, okay? So let's say like, okay, so here goes. First thing that we do is just pretend that we're not working with polar coordinates at the moment, and just pretend that was like y equals 1 plus cosine x. So draw it in rectangular coordinates. So to do that, in another video, I talked about the sine and cosine waves, how they have they're periodic, they have a period, how you can use 5 points to sketch them, and so on. And so I'll start off by doing this one that way, but I'll save on some of the explanation for it, okay? So what this would be is, imagine you had the graph of cosine with a vertical shift of 1. Remember, when I do this, I'm ignoring the fact that it's really in polar coordinates, all right? So that'd be like theta on the horizontal axis, r on the vertical axis. In rectangular coordinates, there's a horizontal and a vertical coordinate. So the period is 2 pi, and I'll use 5 points to draw it. So I need to divide this space into fourths. So pi over 2. Divide it in half, divide it in half again. This is your quarter, so 1 pi over 2, 2 pi over 2. This next point must be 3 pi over 2. And 4 pi over 2, that's 2 pi. So once you divide it, you identify the period, divide it in half again. That's dividing it into fourths. Here's your fourth. There are 4 fourths right there. Other than that, imagine if you took the cosine wave and vertically shifted each point up. Well, I mean, that's all it is. The period is no different. Okay? So I'm going to get something like this. So let's say 1 and 2. Okay? So my first point is going to be here. The next one here. Then here. Then here. Then here. So I have my points. And then draw the shape. Okay. Right, okay, so there's what you should recognize. Oh, that looks a little crooked, but I'm not going to redo it, all right? More or less the cosine wave, but for this vertical shift. All right, that looks pretty sloppy, but I'm going to have to go with it. Now, it looks good enough to do this. Suppose that I took these points in that pattern, and I converted them to polar coordinates. All right, imagine if you did that. Now, if you've never seen that done, it is a little hard to imagine, but here's what I mean. So imagine like right here, I'm going to plot like all of these points in polar coordinates. So this one right here, so theta is 0 and r is 2, okay? So let's see, I should be consistent with my scale. Let's say that's 2, so like 1 inch is 2, half an inch would be 1. There's that same point in polar coordinates to start with. Okay, all right, so there we go. That's r and theta being 2 and 0, I'll say degrees. Now from here, imagine if you did this. What's the trend on the graph as theta goes from 0 to 90 degrees? R starts at 2 and very gradually diminishes until it's 1 when you're at 90. So, okay, let's put this point. There is 1 for r, 90 degrees for theta. What would it have to look like if if it did this, where as I tilt my angle towards 90, r very gradually gets smaller until it's 1 at 90. There'd have to be like some kind of an arc right here. Okay? That's what it would mean. All right. So that's what I'm saying about that one. Now, you can imagine this. Is it true, say if I had, here's this protractor established with my angle. Is it true that as I tilt my angle towards 90, that the distance, the radial distance to the curve, very gradually shrinks? Yeah, I mean, as I tilt my protractor up to 90 degrees, the distance to the curve does get smaller. And then when you're at 90, it's 1. So it shrinks from 2 to 1. So that's why there has to be an arc like that. Now, just to make sure this matches up, I'll say this section on that curve, if converted to polar coordinates, corresponds to this section on the polar curve. And I'll just do that one section at a time. Now, what about the next one? As you tilt from 90 to 180 degrees, r diminishes from being 1 at 90 degrees to 0 when you're at 180. So what would that look like? I have to use my imagination a little bit, but imagine I'm tilting towards 180, but r has to close in to 0 by the time I get to 180 degrees. It'd be something like this. Okay? Now, is that consistent? So I take my ruler. Is it true that the more I tilt to 180, the more my radial distance diminishes? But by the time I get all the way to 180 degrees, it's closed in at 0. Okay? All right, so what I'm saying is these points in that pattern, if converted to polar coordinates, give you this section. As I tilt my angle from 90 to 180 degrees, the radial distance closes in from 1 to 0. Okay. Now, so once you do a few of them, that's how all of them are done. All right, but I'll go ahead and I'll do the others. I'll complete this picture. So what happens if you turn from 180 to 270? Well, here r will increase. R will increase from 0 to 1. So I know by the time I get to 270 degrees, r is going to be 1. So that's going to mean you end up at that point. But if you start with r being 0 and very gradually gets bigger, then it'd have to be something, again, kind of like that. It's true. So here's 180, r is 0. Tilt a little bit. Okay, r is a little bigger. Tilt a little more. Okay. Yeah, the more I tilt to 90, the further, in fact, all those points are out there. Until I get right there, where that point is, 1 for r and 270 degrees for theta. All right. So this section of the rectangular graph, if you convert those points and that pattern to polar coordinates, you will get this one. One last one. From 270 to 360, as you tilt your angle from 270 to 360, r will very gradually increase until it's 2. It will increase from 1 to 2. So you'll end up back there. Okay? I keep emphasizing the same thing as I've done this and as I've talked about it. That, just look, tilt the ruler. The more I tilt towards 360 degrees, the further the point is out there. Okay? The radial distance is getting bigger. That's what, here, r is 1. Then it's 1.5. Then it's 2. You're seeing that happen. So, okay, my final answer, in that I converted this section, those points, that pattern, to polar coordinates gives me this. That's the full picture, okay? So the curve in polar coordinates, r is equal to 1 plus cosine theta. It is right there, okay? This curve has a name. You can look it up if you want to. called a cardioid. Okay. You can also generate the graph on Wolfram as you work through the assignments and you try to graph them on your own with paper and pencil. You can check the graph on Wolfram, and it's hand drawn. I'm sure it looks a little nicer if you draw it on Wolfram or with a calculator or something like that. But that's about as good as it's going to look on paper, just freehand. Okay. All right, now, but as you get the bird's eye view of this, can you just understand the conversions? That's what I need to make sure you're getting. Convert the pattern, the points, everything from rectangular to polar turns this into this. Okay. All right, so let's try another one. Just kind of a complementary problem. One that we can work in a similar way, but ends up looking quite a bit different, and that's this one. Okay. So graph it in polar coordinates. Now, I'll take the same approach. First, can I graph it rectangular? And then can I convert those points in that pattern to polar coordinates? So that would be it, right? So let's do this one rectangular coordinates by noticing that it would just have to be the sine wave, but the period would be different. Okay? So if I'm drawing this rectangular coordinates, theta on the horizontal axis, r on the vertical axis, it will have a period of 2 pi divide by that number. That's what we figured out, right? That number right there, that 2, alters the period of the sine wave. In this case, it makes it 2 pi over 2. So the period is pi. Now maybe you remember in that I posted another video and I said, well, the sine wave period is normally 2 pi. You can sketch out the same 5 points, the 1s and 0s, and they're all separated by 1/4 of the period. That's not going to change with this one. So, say, all right, arbitrarily, that'll be pi. Divide this into fourths. And, you know where to position your points. So pi, and I'll divide that in half. Pi over 2. I'll divide that in half. Pi over 4. And I'll count by pi over 4. 1 pi over 4. 2 pi over 4. 3 pi over 4. 4 pi over 4. So that tells me where my 1s and 0s are going to be. So could you take the sine wave, it's 0, 1, 0, negative 1, 0 on this, with pi being the period. Okay, so I'll get 0, let's put 1 right there, 1, 0, negative 1, 0, right? And there it is, that's how it's going to be in rectangular coordinates. Okay. Now, once we get the points, so we knew what the shape was going to be from the beginning. Whenever I started this, I knew the answer I was going to get would be the sine wave. It was just a matter of, in this problem, of figuring out where the points were. I got one at pi over 4 and 1. I got one at pi and 0 and so on. All right, now, if our goal was to graph this in polar coordinates, the objective now would be to take this graph, those points being in rectangular coordinates, and converting them to polar. So all right, so here's our second task. Convert that to polar coordinates. Okay? All right. Convert it to polar coordinates. Now, we'll do it one section at a time. Just like the last one. Okay? So we'll divide this into sections. So 0 to, so that's 45 degrees. Here's what has to happen. Your initial point is 0 for r, 0 for theta. In polar coordinates, that would be here. Your curve is such that as you tilt from 0 to 45 degrees, r very gradually increases until it's 1 at 45 degrees. So I'm drawing these freehand, but I'd like it to be as nice as it can be. So I'm going to go ahead and say, all right, that line right there, with my protractor, that's 45 degrees. So I think, let's say that's 1 right there. So 1 inch, that'll be 1. what's this curve going to have to look like if, as you increase your angle from 0 to 45, r very gradually gets bigger? It have to be something like this. Okay, is it true? So here's 0 for our theta. And what happens if I tilt towards 45? The radial distance to the curve gets bigger. Why does it have to be that way? Well, because on this, r is 0, and it gets bigger and bigger and bigger and bigger until it's 1 when you're at 45 degrees. So yes, on that curve right there, that arc, the r coordinate does very gradually get bigger until it's 1 right there at 45 degrees. So okay, so like that converts over to this. I don't know about the rest of it, but so far this section, those points, that pattern, if converted to polar coordinates, will give you this. Okay, now let's continue. So what happens if I were to continue to tilt? Say tilt from 45 to 90. Well, by the time you get to 90, r is 0. So we're going to get back here. But r will, as you tilt from 45 to 90, very gradually diminish from 1 to 0. 1 to 0. So that's going to be like kind of a symmetric arc like that. Okay, is it true? Well, all right, there's 45 degrees, r's 1. Tilt a little towards 90. The radial distance is a little bit less. Tilt a little more. Okay, the radial distance is closing in. It's getting smaller and smaller and smaller as you tilt from 45 to 90 degrees. So this section, those points, converts to this. Keep going. All right. So as you, what's that, 90 to 135. Okay, so when theta is 90, r is 0. As you tilt towards 135, r will get more and more and more negative. Okay, so let's put that angle on here for reference. So here is 135. All right, so like, like that. All right, so there's theta is equal to 135 degrees. Whoops. Okay, so as I'm like in here, right, tilting from 90 to 135, r becomes more negative. So think about that. Until like when I'm at 135, r is -1. Well, at the very least, that means this point is on there. Okay, so right there, that point is for r and theta. That's going to be -1 for r, 135 degrees for theta. But it's going to mean that I'm going to have to go like this. Okay? Because like imagine, I go this way, r is more and more and more negative. That means that the radial distance back this other direction is further. So then I'm going to get that. All right? Just project backwards. All right, so is it true as I tilt my angle from 90 to 135, the radial distance is backwards more and more and more to 1, right? -1 means backwards, so we get like that. All right, so those are negative r's, but I know we've learned about that at some point. For all those points, the r is negative. Let's do this last section, 3 pi, so 135 to 180. As you tilt from 135 to 180, r begins at -1. As you tilt this way, the radial coordinate diminishes from -1 to 0. So imagine like you're out here, the more you tilt that way, the r coordinate closes in until it's eventually 0 at 180. So that would close in this loop right here. Okay, so then that would be this fourth section. Now, so I don't know to you if that looks incomplete or not, but the truth is this one is a little bit incomplete. All right, like this is not enough to draw that entire thing. We would have to look a little bit further. So I'll show you what the next few points look like. Ultimately, I'll let you do this on your own. I mean, eventually you're gonna have to try to do it on your own. So say I was going to find the next point over here. So what am I counting by? Pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6. Yeah, you can keep going. And of course, it's periodic, right? The whole idea is that it keeps going. So like you could do this next section, and that'd be like from 180 to 225, okay? And you'd say, well, as I tilt from 180 to 225, R increases from 0 to 1. So it's like 225, right? You know, if this is theta is equal to 225. By the time I'm there, R is 1. But what's it look like if R increases as I tilt from 180 to 225? Well, we're going to get an arc like that. Okay? And there's that point, right? 1 for R, 225 for theta, this point right there. So now that's the last one I'll do. I'll say that's section 5, and you know, it gives me this. But yeah, I'd have to, really to get all of it, I'd have to keep going even further than that. And so the finished product looks like this. It has 4 loops on it. Okay? But you know, you'd have to continue this to see it. But I mean, if you can graph one section or one loop, you can probably do the others. All right, that's what you'll end up with. Okay, so we saw like 2 very, I mean, I don't know, I'd say they were different. They look a lot different, but I did them the same way, right? I take that and I convert it the same way. All right. Okay, so that's this main strategy in lesson 20. There's plenty for you to try there. Go to Wolfram Alpha and use the polar plot command, and you can verify any of the graphs you try to draw by yourself.